Hello, stat students. Today we're going to finish up section 11.1 talking about chi-square goodness of fit tests. So let's take a look at another example here of running a chi-square goodness of fit test. Biologists wish to cross pairs of tobacco plants having genetic makeup GG, indicating that each plant has one dominant gene and one recessive gene for color, and then each offspring plant will receive one gene for color from each parent. So if you remember Punnett squares, here are the possible results. Now this square suggests the results are, 1/4 of the time we'll get, capital G, and 2/4 of the time we'll get one of each, and 1/4 of the time we'll get lowercase g. So that would lead to 25% of offspring that are green. And then 50% will be yellow-green, that's those two, and 25% will be albino, is what that leads us to think. So to test this hypothesis, the biologists mate 84 randomly selected pairs of yellow-green parent plants. Now of the 84 offspring, 23 were green, 50 were yellow-green, and 11 were albino. So do these data differ significantly from what they predicted? And you can see that maybe they do, because that's a little bit low, especially compared to that. We would think those would be the same number. So let's carry out the appropriate test at the alpha equals 0.05 level. So state plan to conclude. So here's how we can word this is one way to word our hypotheses. Proportion of green is 0.25, proportion yellow-green is 0.5, and proportion albino is 0.25. The alternative is that the biologist predicted color distribution isn't correct. That is, at least one of the stated proportions is incorrect. Plan. We're going to conduct a chi-square goodness of fit test if our conditions are met, which are random. Yes, the data come from random sample. Large. I think that's an answer from a different problem, but basically it's a random sample of 84 randomly selected pairs. There it is, randomly selected pairs of parents. Large sample size. Now again, we don't look at the observed values, we look at the expected values. All expected counts need to be at least 5, and you can't just say that they are, you have to show that you actually calculated them. So 1/4 of 84 is 21. Half of 84 is 42, and 1/4 of 84 is 21. So we would expect 21 green, 42 yellow-green, and 21 albino, and all of those are at least 5. And then independent, individual offspring inherit their traits independently from each other, and we are sampling without replacement, so it's reasonable to assume that there are at least 840 tobacco plants in the population we selected from. And then here's a table of observed values and expected values. So you can see way less here and slightly more here. Then we calculate our chi-squared statistic using this formula, or we can have our calculator calculate it, but here's what it would look like when we plug the numbers into the formula. We add those up and get 6.476. You can use your calculator and 2 degrees of freedom to find our p-value. So that looks like this. I would type into list 1 my observed counts, and then here's list 2 the expected counts. And then I go stat, test, and then towards the bottom of the list, option D is a chi-squared GOF test. And then I'm going to tell it my observed list is list 1 and my expected list is list 2. Again, these are counts, not proportions. There were 3 possible categories, so 3 minus 1 is 2 degrees of freedom, and then I hit calculate, and there's my chi-squared statistic, there's my p-value, and there's the degrees of freedom. Okay, and then because that p-value is less than 0.05, we reject the null hypothesis, and we have convincing evidence that the biologist's hypothesized distribution is not correct. All right, now let's talk about that other thing you see on your calculator screen right here. What are these numbers? So those numbers would help us do a follow-up analysis. So when we do a chi-squared goodness of fit test, the null hypothesis that a categorical variable has a specified distribution. Now, if we get a statistically significant result, we can conclude that our variable has a different distribution. When this happens, you might want to start examining which of the categories show large deviations, because all we can say that it's different than we thought. But a follow-up analysis will allow us to kind of analyze or talk about what's different about it specifically. And how you do that is you look at the individual terms that are added together to produce the test statistic. These are called the components, okay? So basically, when we did this calculation here, these three numbers were the components that contributed to this chi-squared statistic of 6.476. And you can see that this was the biggest component. That means this is the observation that deviated the most from the expected count, basically. And because it contributed the most to the chi-squared statistic. So what we would do is we would then, in a follow-up analysis, talk about the fact that, our observed distribution was different than expected, largely, in fact, to getting much fewer albino offspring than would be expected. Now, your calculator has these three numbers right here. You can see these three numbers right here are in this list on your calculator under this contribution. Now you can see it cuts off the list. We can only see the first two numbers. So when you're on the screen, you can press left and right to scroll between the numbers, and they're going to be in the order that you entered your list in. So that's how you can get those numbers from your calculator. Now, you should only do this type of follow-up analysis and discuss these things. When you are doing the analysis, make sure you talk about direction, not just which one's the largest contributor, because whether you get more or less than expected, these will always be positive. So you have to say we observed less albino than expected. And like I mentioned, you can find it on your contribution list on your calculator. Now, this follow-up analysis is not part of the state plan do conclude. So you should only do a follow-up analysis if it specifically asks you to. So on the 2008 AP exam for response question 5 did, and it was a question about studying moose populations and where they were hanging out. And we, in part A, did a 4-step process, basically. And then in part B, it says, relative to the proportion of acreage, which habitat do the moose seem to prefer. And to answer that, you would use the contributions to the chi-squared statistic to discuss which ones were more popular than expected. Let's take a look at another example here that I'd like you to try. This is one that I think is very interesting. So in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month actually has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is the cutoff date for youth leagues in Canada, and many NHL players come from Canada, players born in January will be competing against players that are up to 12 months younger than them. So that means the older players, at that young age tend to be bigger and stronger and more coordinated. And because of those advantages, they get more playing time, more coaching attention, and then have a better chance of being successful. So this was his theory. So to see if birth date is related to success, and we're going to define success as whether a player makes it into the NHL or not. We look at a random sample of 80 NHL players from the 2009-10 season, and we record their birthdays. Instead of just doing 365 possible categories, we're going to group them into quarters of the year. So 32 of those 80 players ended up being born in the first quarter of the year, 20 in the second quarter, and 16 in the third quarter, and 12 in the fourth quarter. So, do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? I would actually like you to give this one a try. Try writing up the 4-step state plan do conclude process, and then press play when you're ready to check your answer. All right, so let's take a look at what you got. This should be what you get from your calculator, but there's a lot more to do than just that. Here's what your write-up should look something like. So we can see here's two different ways to write the state portion, either description or using, our mathematical notation. If you're using this notation, make sure you define P. Our plan, all the conditions are met. There were more than 800 NHL players that season. There were 879. In large sample size condition, remember to check your expected counts. They're all 20. And then the do, our calculator gives us this value. One way you could write it is you could show the start of the formula and then like a plus dot dot dot. And using degrees of freedom 3, we get a p-value of 0.01, which means we reject the null hypothesis. So we do have convincing evidence that the birthdays of players are not uniformly distributed. Notice though, this isn't what Gladwell's claim was, but this is where I'd stop with this problem. He said, though, that it wasn't just that it wasn't uniform. He said specifically that NHL players are more likely to be born early in the year. Now, to answer that question, we would do a follow-up analysis, and I'd like you to give that a try. So press pause and then press play when you're ready to check. And here's what you should get something like when you do your follow-up analysis. Notice I talk about the direction, less players in that fourth quarter and more players than expected in the first quarter. So that is it for section 11.1. So make sure you finish up your 11.1 homework and, of course, email me with questions.